This will be the second video of my confounding videos, and the first one was all about just an overview of confounding. This one's about detecting it in your data, and the other one will be about how to control for it. So just to start with, to generate a list of potential confounders, some of the best ways to do that are to look at the existing literature. So if you're interested in smoking and lung cancer, find some recent articles on smoking and lung cancer and look for what they adjusted for in their models. So they might say they adjusted for something like age, and in that case, that's some good evidence that that's a confounder. That shouldn't be your only source of potential confounders, but that's a good one. There's also universal confounders that I'll get to, and brainstorming confounders using a directed acyclic graph. So there's some universal confounders, and I have that in quotes because it doesn't necessarily apply to everything, but things like age, sex, and socioeconomic status have really broad-reaching impacts on your disease susceptibility to a lot of diseases, and also they're related to a ton of exposures. So even if there isn't precedent in the literature for this, sometimes people try and control for these just to see if they're a confounder, even if they don't really have a ton of justification. And the last one is using DAGs, and that one's the best one. So let's just say we have this hypothetical exposure and outcome, and there's all these other variables that we think might be playing a role in this relationship. So we would plot them out and plot this relationship and start to brainstorm which one of these might be confounders. So some various ways to choose what might be a confounder. Some people choose all that are causally related to the exposure. Some choose all that are causally related to the outcome. So these ones here, causally related to the exposure. The reason none of these are is because there's no arrow going towards the exposure. They're all going to the outcome. And here it's those that are only related to the outcome. So this one isn't included. There's also those that are related to the exposure or the outcome, which accounts for all of them, or the more conventional definition, only those that are related to both the exposure and the outcome. So once you have this list, it might be pretty massive. You might be wondering, why don't we just control for them all? It can be an issue if there's too many confounders and a low sample size. Depending on the model you choose, it might not be able to converge, or it might give really unstable estimates. You can get significant covariates by chance, so you might find some of these relationships are significant because the more relationships you have in a model, the more likely you are to find something by chance, something called multiple comparisons. And there might be issues with collinearity if a lot of these confounders are contributing the same information. And also, some of these potential confounders might not be confounders, because you'll notice that some of the criteria we used were just being related to the exposure or just being related to the outcome. And you'll remember that a confounder, to be a confounder, it needs to be causally related to the exposure or associated, causally related to the outcome, and not an intermediate on the path from the exposure to the outcome. So our various ways of detecting confounding really focus on these three criteria. So for example, something called propensity scores is looking at whether there's a relationship between the confounder and the exposure. Backwards elimination, or your typical model building process, is looking at whether the confounder is related to the outcome. And change in estimate is assessing this exposure outcome relationship and how the confounder affects that. So just getting right into it, I guess a first one we can talk about is detecting confounding based on those that are related to both the exposure and the outcome. So one way we could do that, if we're looking at, say, alcohol as a confounder that's related to liver disease or fatty diet and liver disease. Yeah, I'll just describe that. So we hypothesize that fatty diet might be related to liver disease, but we also think that alcohol might be related to fatty diet, where those who engage in a healthy diet might be more conscious about their alcohol consumption, so there might be a relationship there. And alcohol is also established as related to liver disease. So determining if alcohol is related to our outcome, so investigating this relationship, we have this 2x2 table where we have those that engage in high and low alcohol and those who had and did not have liver disease. So just a brief way to look at that relationship, we can do an odds ratio, and it comes out to 9.3. So those who have high alcohol consumption had much higher odds of liver disease than those who don't. So we are able to determine that this relationship exists. We don't know if it's significant, but we have a pretty good idea that it exists. So and now we're looking at this relationship, alcohol and fatty diet. So it's same kind of idea, and we're able to find an odds ratio, and we found that those who engage in high alcohol consumption are also 2.25 times more likely to have a fatty diet. Another way is just looking at whether alcohol is related to the outcome, and the way people typically do that is just including confounders in the modeling process. So just a brief overview of backwards elimination. It's when you start with a maximal model, so everything you think might be involved, and remove things one at a time, starting with what is least significant. So this is our full model, and we can see that we don't care about the intercept and exposure. They're not what we're removing. We're going to force those into the model, and they're significant anyway. But among these three confounders, the one that is the least significant, and that means it's least likely to be related to the outcome, we can get rid of that one first. And now you'll notice that things changed, and significance of what remains changed, but now the second confounder is the least significant and has the highest p-value, so we kick that one out. And now we're left with one, and we typically use a more liberal p-value for this process than 0.05. So here, this would be an example of us determining that this confounder 1, CFVA is confounding variable, it's this short form, is related to the outcome. So that would be one way of coming to that conclusion. It has some issues though. You can end up keeping too many. Just because it's related to the outcome doesn't mean it's a confounder. It could just be related to the outcome and have nothing to do with the exposure. And also, just because something's significant in the model doesn't make it a confounder, and if it's non-significant, it might still be a confounder. So it's better to have other ways of figuring this out, and I'm going to cover some other ones now. So another way of getting some evidence that something might be a confounder is looking at whether it's related to the exposure, and one way we can do that is with propensity scores. So the idea with propensity scores is you're measuring the exposure as the outcome of this regression, where typically we would have the outcome, the intercept, and the exposure and covariates. That's what we're used to seeing. But propensity scores flips that, where now the outcome is not involved, but we're using the exposure as the outcome. And these are various confounders that we think might be related to the treatment someone gets. So just to make this a bit clearer, if this treatment is, say, a very invasive treatment, like open heart surgery, compared to something like antibiotics, some things, if we're modeling this as the probability of getting open heart surgery, some things that might influence that are things like age, severity of the infection in the heart, and just other things to do with frailty like comorbidities. Those are all things that are going to help the doctor decide, or it's going to influence the probability that they're going to get the more invasive treatment. And that's basically what we're doing here, where we do a modeling process where we keep the confounders that do significantly predict exposure, and then we come up with this model. We generate a model. Now these are just inputting the coefficients that the model would get. And now if we input everyone's data for confounder 3 and confounder 4 here, it will spit out a probability of exposure for each individual. And now that is a data point that is in our data set applied to every individual. They have that the same way they have a confounder status and an exposure status. They have a probability of exposure, and we can include that in the model as a covariate. So now this is our model as we're used to seeing it: probability of the outcome, intercept, and we have our exposure, and now probability of exposure. And yeah, some issues are the main one, as I was just looks more obvious here, is if the exposure, if some of these probabilities are too related to the exposure, so it's like this one confounder completely describes whether you're going to get the, like, let's just say only people over 50 are eligible to get this treatment. Then all of a sudden, age completely describes your likelihood of treatment, and you have a collinearity problem. So that's one problem with modeling this way with propensity scores. Some advantages are that any confounders contributing to confounding by indication can be eliminated with one variable. And also, a lot of people in the clinical world who don't understand a lot of the other methodologies in epidemiology seem to really trust this one because they understand it. Yeah. So this third one is probably one of the most powerful ways of detecting confounding, and that's looking at whether the exposure-outcome relationship differs when stratified by this confounder compared to when it's just crude and you don't stratify by that. So I'll show you a bit about this. So if alcohol is confounding this relationship between fatty diet and liver disease, two things will be true. The unadjusted odds ratio, and I'll show that, just hold on, I'll show you that in a second. It'll differ from the odds ratio between strata. So it'll differ when you separate everyone who's a high alcohol consumer and a low alcohol consumer. And also the odds ratio in the high alcohol and low alcohol strata will be similar. So that is hard to hear just as words, but once we do an example, it'll be a little clearer. So here is our 2x2 contingency table where we have someone's diet and their liver disease. And we can see that this is the crude estimate. People who consume high alcohol and low alcohol are scattered throughout this table. They're not separated. We get an odds ratio here of 2.9, so those who have a fatty diet are almost 3 times more likely to get liver disease. But if we take everyone who's a high alcohol consumer and put them in one table, then we can get an odds ratio where we see it's different. It was 2.9 before, but now just among the high alcohol people, it's almost gone. It's just an odds ratio of 1.2. And we do the same thing with those who have low alcohol consumption. We give them their own table and their own analysis, and that comes out to 1.3, which is very close to the high alcohol strata. So we can see that the relationship between fatty diet and liver disease almost goes away when we control for alcohol. So when we look at it separately among the strata of alcohol consumption. Yeah, so that gives some indication that alcohol consumption was explaining almost all of this relationship. So just putting these facts together, we found a crude OR of 2.9. The high alcohol odds ratio was 1.2, and the low alcohol odds ratio is 1.3. So that just kind of illustrates what I said before, where it meets all of those criteria we said, where the odds ratio, the association essentially goes away once you separate the strata of alcohol consumption, indicating that alcohol was probably a confounder, and the other criteria you got to look for is that it's a similar odds ratio among the two strata. So I'll show you just the other ways that this might have come out. So if we found out that the crude odds ratio, the high alcohol odds ratio, and the low alcohol odds ratio were all similar, that would be an indication that there's no confounding happening really. Alcohol is not really influencing this relationship. And the more extreme example, if we found that these two differed from the crude odds ratio, but they were very different from each other, that's an indication that there might be effect modification going on or interaction where alcohol consumption and fatty diet have this synergistic effect. Yeah, so that's what you'd look for when doing this analysis. And although that one before was probably one of the more convincing ones for looking for confounding, probably the most common one is change in estimate. And there's 2 ways to do that. There's the mental Hansel method, which is pretty good. It's useful if you don't want to control for more than one confounder. It's kind of archaic, but something that does a very similar thing is just classic regression, just including your potential confounder in a regression. So the basic idea of change in estimate is, so we have 2 potential confounders here. We would remove them one at a time and note the change in the exposure coefficient. And we would say something like, if the exposure coefficient changes by more than 10% when one of these are removed, it was probably a confounder. So just going through that process, step one, you just begin with all of the covariates, noting that when everyone's there, the exposure coefficient is 3.56. Then we removed confounder 1, and we saw that everything changed, and the exposure coefficient went from 3.56 to 3.3, so about an 8% change. And then we add confounder 1 back and repeat it, removing confounder 2 now, and the coefficient went from 3.56 to 3.8, or a 6% change. So confounder 2 had less of an impact, so that's the one we kick out first, rather than kicking them both out at once. So now we have confounder 1 left, and we have a coefficient of 3.8, and kicking confounder 1 out, we can see that the exposure coefficient goes from 3.8 to 4.5, which is a 15% change. And that exceeds this criteria we put as 10%, so we'll retain this one as a confounder. So just another thing, we're assuming this is linear regression, where you just look at the change in the coefficient. If it was logistic regression, you wouldn't look at the coefficient, you would be looking at whether the odds ratio changes by more than 10%, so you'd be exponentiating these before you would compare. And once you decide it's a confounder, its significance is irrelevant. You'd force it into the model.